So let's get started. Okay. First, before we start, okay, just want to remind you that the homework 4 has been uploaded, but which actually include this little chapter. We haven't we didn't get to finish this chapter last time due to some hardware issue. It turns out, it's a connection issue. It's really not it's not like anything is broken, but anyway, okay, let's try to catch up the progress. Okay, my plan is to cover to finish this chapter, and we'll also talk about the windowing, okay, which is actually in the textbook like one chapter, ahead of this one. Okay. So let's we talk about the basic idea of this this randomized incremental algorithm. Basically, like when a new inserted point is inside the this three-dimensional Voronoi diagram. Nothing needs to be done. Okay, but when it is outside, okay, we should be able to, from that particular point, okay, see several faces, and those faces will be the ones that need to be removed, and then we need to add a few new faces, okay, that are like adjacent to the PR, okay, the new inserted point. Okay, so but the issue is how do we check the the faces that are visible. Okay, so as we discussed last time, if we do not have a efficient way to deal with that, then we are going to end up with n squared complexity algorithm, okay, to finish this insertion process. But that's too costly. Okay, so the idea is to maintain a conflict graph. Okay, this conflict graph, okay, is a bipartite graph. Okay, when the bipartite graph means like your nodes in the graph can be divided into two sets. Okay, two sets, and the edges appear only in between these two sets. Okay, from one node in one set to another node in a different set. Okay, so you don't have any edge, inside. One of these two sets. No, that's the idea of the bipartite graph. Okay, so this conflict graph. Conflict graph. I think when we were here, that's the time when the computer shut down on me. Okay, so let me repeat. Okay, so as you can see, okay, because it's because we are talking about like incremental algorithm, so we can assume at a certain time, okay, we already have a conflict graph, and then we need to talk about how to insert a point. Okay, so at the beginning, okay, well, not at the beginning, I should say like the conflict graph. Okay, before you insert a new point, okay, you have two set of nodes, just like I described. Okay, the first set is the points that will be added. Okay, so if you already add, okay, P1, P2, P3 up to PR minus 1, then the point, okay, the set of points will be PR, PR plus 1, blah, 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 to Pn, assuming we have n points to deal with. Okay, so you can imagine, okay, at the beginning, we have many these points, okay, very close to the number n, right, the number n. But as we insert the point one by one, the size of this point set decrease, okay, decrease gradually until it becomes 0 after you finish the all insertions, okay. And on the right hand side, these nodes, each of them represent a facet, okay, represent a facet. And you can also imagine, okay, because at the very beginning, okay, at the very beginning, well, if you try to insert one node, it's impossible to create any facet. You need to insert at least 4 nodes, right? You need to insert at least 4 nodes to really, well, the 3 node create facet, but it's not 3-dimensional either, right? So in order for us to consider like a real, 3-dimensional convex hole, then you need at least 4 points, right? So when you have 4 points, as long as those 4 points are not on the same surface, as long as they are not on the same plane, then, okay, you would have 4 facets, right? You would have 4 facets to start with, okay? So, so basically, okay, as you insert more points, the number of facets may increase. So you can imagine, okay, as the insertion process going on, okay, this number of points decreases and the number of facets may increase, right? May increase. Okay, so we call, and we have some edges between these 2 sets. Okay, that is, when a point is able to see certain facets, we have an edge between them. Okay, so for example, like given a particular point, say this is PT, okay, all the facets it can see, okay, which include this one, these 4 facets, we call that the F conflict of this FPT, okay. And similarly, okay, when given a facet, okay, the point that will be able to see this facet, for example, for this F, you can see we have 3 edges that point to the lowest 3 points, and we call that point as the conflict point set of F, denoted as P conflict F. Okay, so this is very important, okay, because we are going to use this later on, okay, later on. So it looks to us that, intuitively, it looks to us that, okay, if you want to maintain this conflict graph, it looks like it's expensive. It looks like it's expensive because obviously, like when you insert a point, okay, it looks like you are doing additional work, okay, because, well, why do we need to maintain the other conflict relations? Why don't we just focus on the point that we want to insert? Okay. So let's discuss the initialization and how do we maintain the conflict graph? Okay, the initialization of the conflict graph. Okay, as I said, okay, at the very beginning we have we start from the 4 points that are not on the same plane. Okay, so okay, we start from the 4 points that are not on the same plane. Okay, it should be noted that for 4 points to happen to be on the same plane, the chance is very low anyway. Okay, so we start from the first 4 points. Okay, that we can obtain. Okay, from the list. Okay, if those 4 points happen to be on the same plane, we switch to a different 4 points, basically. Okay, so basically, okay, so say when we have the the first 4 points, you could imagine, okay, this point set will be n minus 4 points, right? Because the point sets are the point that will be inserted. Because now you already, use those 4 points, so you should remove those 4 points from these point sets, right? So it's going to be n minus 4 here. I mean, for this set of points, okay, the size of the set of points, and okay, and you could use your high school math to basically to directly create those, because 4 points for such you can only come up with kind of like a pyramid shape, right? Pyramid shape, which has 4 faces, right? So that shouldn't be too difficult to calculate. So you see, for the point set, you have P5, P6, blah, blah, to Pn. But for the faces, you are going to have 4 faces. Okay, so since you have 4 faces, and you have n minus 4 points here, so checking the conflict between them, okay, for each of the point, you check if it is conflict with those 4 given faces. Okay, it takes pretty much constant time, right? Because the number of faces is fixed to 4 anyway, right? But you have n minus 4 points left here. So the initialization, obviously is linear, right? It's linear. Okay. So this linear initialization, okay, it's not too bad, right? It's not too bad. But how about the maintenance? Okay, when we add a point to your convex hull, okay, what do we do to the conflict graph? Okay, when point PR is added, the faces in F conflict PR, the faces that conflict with PR, as I mentioned earlier, these faces, because they are visible from PR, so they need to be removed, right? They need to be removed. So those can be done easily by the help of the conflict graph, which is good, right? Okay, but and also for the faces, after you remove these faces, okay, for some of the faces, you need to create these new faces, right? So these new faces, you have to also create them and add to this to the faces list, right? To the faces list. But how about these newly inserted faces. I mean, they may be conflict with the other points that will be added at a later time, right? So what do we do about them? Okay, because now we have some new faces that we need to determine, okay, if they have any conflict with this remaining point sets, okay? But do we need to look at all the point in the point sets to see if they conflict with this new inserted faces, okay? It turns out, okay, to be, unnecessary, okay? So suppose we add a PR, and I mean from this figure you can see F2 is visible to PR, right? So F2, okay, will be removed, right? It has to be removed, okay? So we will create a new face. Okay, we call that face F, okay, which is marked in gray color, right? In gray color, okay. So, so for this new face, as I said, okay, you need to check if some points conflict with this new face, right? So, the most important concept here is this, okay? If any point is able to see this face, if any point is able to see this F, okay, those points have to be able to see this edge E first, right? Because edge E is still part of this new facet, right? Right? This should be obvious, right? But okay, if those points can see this edge E, okay, those points, okay, before we insert PR, those points must conflict with either F1 or F2, right? Right? Okay, if a point is able to see this edge E, okay, either it's here or it's somewhere here. Otherwise, I mean, if you are inside here, you are not able to see this edge E anyway, right? Okay, so remember, like in a conflict graph, okay, you can get this given a face, you can find the point that conflict with that face too, right? Okay, so what you really need, okay, to check the points that you really need to check, okay, would be okay, P conflict F1 and the P conflict F2, okay. So these will be the points you need to check, okay, to see if they conflict, if these points will be conflicting with this new face F. Okay, instead of checking the whole set of remaining points, you just check this subset of points, okay, which turns out to be not that many. Okay, it turns out to be not that many. Okay? So the conflict points of F can be found by testing the points in the conflict list of the two faces, F1 and F2, that were incident to the horizon edge. Okay, for this edge, I mean, yeah, I think last time I told you about that. This is called horizon. Okay, horizon edge, E in CHP R-1. So you have a more systematic way to maintain the conflict graph. Okay, from the beginning to the end. Okay, so which is very convenient. Okay, so that's about it. Okay, this is the algorithm for the convex hull. Okay, I don't think I need to go through the detail of this algorithm. Basically, it's just like what we discussed. But one thing you can see, okay, we will do a random permutation here. So you can see that this is also a randomized algorithm. Okay, and then for the first 4 points, I mean, we just create the first convex hull and with 4 points, and we also create the initial conflict graph. Okay, so find the 4 points. Okay, in P that to form a terhastron. Okay, I mean, this is like just kind of pyramid. Okay, and then okay, we include the first 4 points, and they compute a random permutation, and initialize the conflict graph, and then I mean we do the insertion of the points one by one. Shouldn't be too difficult. I mean, basically it's just what we just discussed earlier. Okay, but okay, the last thing. Okay. This algorithm, okay, computes a convex hull of set of n points in 3-dimensional in n log n expected time, okay, and the expectation is with respect to the random permutation used by the algorithm. So basically, okay, this algorithm is you can imagine, okay, the time is spent on the maintenance of the conflict graph is really not that much. Okay, it's much cheaper than the n square, right? So unfortunately, okay, this is the only chapter that we discussed, okay, in this class that we will not talk about. We will not discuss how this time complexity come from. The reason is not because like we cannot derive that. It's because it's a little bit too difficult. But okay, this if you are interested, okay, you can check out the section in the textbook that derive this time complexity. Okay, but basically the way I cover this class is that, okay, I cover all the sections that are not with asterisk mark, okay, because the section with asterisk mark are considered more advanced. So I think like, I mean, well, it's in the textbook, but if you are interested, you can check it out yourself. But consider the level of the class. Okay, I'll just skip this. Okay, so and the homework for this chapter, I mean, already announced. I mean, in the last last week. So make sure you will, I believe the due date is 1 week from today. Okay. So now we will switch our attention to a different problem, but this problem actually has also has a connection to the one a problem that we discussed earlier. Okay, remember the range search. I should say range query. Okay, at that time we say it's a range query. Given a set of points, we want to create arbitrary. We want to create a data structure that so that like given an arbitrary query, like a rectangle region. Okay, we can answer how many point. I mean, what points are inside that query region. Okay, very efficiently. We talked about this problem earlier in the range query. Okay, if you already forget about that, I mean, after all, the midterm is 2 weeks ago, right? So I hope these two terms can sort of like recall your memory. KD tree and the range tree, right? You still remember those terms, right? Okay, but now, okay, let's consider a more you can probably say it's a more difficult, but it's more. This problem is also like commonly seen in when you use computer. Actually, okay, so okay, we call this problem windowing. Okay, so for example, okay, when you use a computer, a lot of time, okay, you want to enlarge a particular region in your screen, right? Okay, so so that's windowing. We call that windowing. Okay, actually, windowing has many applications. Okay, for example, when you use the navigation system, think about that. The navigation system contains the whole map, right? The whole map. But when it display to the driver, it doesn't display the whole map to the driver, right? It only display the nearby, street to the driver, right? Because it only has a very small window, right? It only has a very small window. So again, okay, that's the concept of windowing, okay? Okay, or you can say it's a window query, okay? Another possible application of windowing is, for example, in the flight simulations, okay? In the flight simulation, I mean, I don't know if you play the flight simulation games. Some of the, I mean, it used to be a big, much popular branch of computer games. I mean, people likes to drive fly like a different kind of airplane. Okay, actually, I mean, those games are pretty good games because it teaches you how certain skill. Okay, so which is actually, I mean, very not only entertaining but also, I mean, has some educational purpose. But nowadays, because I think flight simulations never materialize in Taiwan, because Taiwan, I think one of the reasons is because in Taiwan, it is very difficult. You pretty much don't have chance to fly a plane, right? Fly an airplane in Taiwan. I mean, we don't have airspace that allows you to to go to the, maybe take the flight like with a pilot, okay, something like that. But in U.S., okay, you have many such opportunities, okay, in some popular sightseeing locations, okay. So you can take the helicopters, you can take like a small airplane, okay. They'll fly you to those sightseeing locations and have bird bird eye view, okay, so which is very nice. Well, I didn't get to, enjoy that because you can imagine, I mean, those service is also very expensive. I think like it's a couple of $100 per person. But because of those opportunities, I think outside of Taiwan, especially in US, okay, a lot of people like to play like flight simulations. And you can imagine in the flight simulations, because all those, I mean, the computer screen will show only the nearby scene, right? But actually, all the scene, okay, are pre-generated and stored in the computer. Otherwise, I mean, it's impossible for those things to generate, why the player fly the airplane. That's, it's just not possible because it takes the speed is too fast. Okay, so again, that's considered a window inquiry. But the flight simulation is different from this map navigation in the sense that in flight simulation, this window query is three-dimensional, which is slightly more difficult because in this chapter we are going to focus on two-dimensional window queries. Okay, another window query like application is CAD/CAM. Okay, for example, like when you are dealing with IC design. Okay, nowadays like the IC chip, okay, is packed with a lot of devices inside, a lot of circuits inside a very small area, right? So when they design the IC, the circuits, actually they need to enlarge this. Otherwise, they wouldn't be able to see like the circuits clearly. Okay. So again, okay, if you want to, arbitrary enlarge, you want to enlarge arbitrary rectangle region, that's again a window query. Okay. So you can see that this window query is a common problem. Okay, common geometric problem. Okay, in different fields. Okay, so can we deal with this? Okay, in our class. Okay, we could, but okay, if you do not restrict the problem a little bit, okay, it is much more difficult than you may think. Okay, because nowadays, like if you try to include how should I say, like a lot of lines with different orientations, that's very difficult. Okay, so let's first simplify the problem. Okay, so we only consider the x-axis to be aligned with the bottom side of the board and the y-axis to be aligned with the left side of the board. So basically, okay, for the window, this is the restriction that we put for the window. Okay, so basically, like we first assume this is x-axis, this is y-axis, and the window, any window. Okay, even though we can have arbitrary window. Okay, in our area of interest, but the window. Okay, this rectangle has to be rectangle region. It has to be rectangle, and the window, the boundary of the window needs to be parallel to the x-axis and the y-axis. Okay, so first we put this restriction. Okay, so that's the query window is an axis parallel rectangle. That is a rectangle whose edges are axis parallel. Okay, we first have this restriction. Second, as I said, okay, if you want to deal with the edge, the edges with all the orientation, that's difficult. Okay, that's difficult. So we assume, okay, any segment, okay, in here, okay, any segment here, okay, is parallel to either the x-axis or the y-axis. Okay, the segments are axis parallel or orthogonal. Okay, so it's going to be something like this. We are going to have a lot of these segments. Okay, let's say we have n segments. S be a set of n axis parallel line segments. Okay, you could imagine each of these segments represent, for example, like if you are talking about navigation system, then each of these segments represent a road, a street, something like that. Okay, so and the window, pretty much, this gray shaded area basically represent an arbitrary window. Okay, that window basically represent like the area of interest. Okay, maybe, well, it's an area that close to your current location. So you need to sort of like display the streets or the roads inside this gray shaded region. Okay, this window. Okay, so this window, okay, is represented by x prime, okay, to y prime. Okay, so we want to have a data structure that can store these segments, so that we can, for arbitrary window, okay, we are able to answer which segments are inside this window, okay, very, very efficiently. Okay, if you look at this problem, you say, oh, well, for a given a set of window, okay, because every time you are doing window query, okay, obviously you will be given x prime, y prime, right? Okay, the x range and y range. So you can, you may wonder like, okay, then how about I just, for every segment, I do this testing if this segment is inside this region or not. Okay, and you say, well, then the complexity is going to be, maybe like n, right, linear to the number of segments, right? N doesn't look too bad, right? Right? In the previous discussions, most of our complexity, is either like n log n, something like that. So, well, linear doesn't look too bad. So you may ask, like, why do we, why can't we just, just check if every segment fall in this region or not? The answer is, first, okay, we want to do it more efficient than that. Okay. Second, think about, for example, think about the navigation system. Okay, say you are driving, maybe, well, this is, well, this should be somewhere near, where is it? Let's say this is East Coast. This should be like North Carolina, somewhere in North Carolina. Say you are in North Carolina driving a car. Okay, if you use the idea like we just mentioned, like check every segment to see if we need to display it. Well, you say, oh, it's linear, it's great. It doesn't take too much time. Do you need to verify if some streets in California that need to be displayed? Doesn't look like so, right? Okay, it doesn't look like it should be the case. I mean, you probably will only need to test certain streets like in this region, right? Okay, not in other states. Okay, so if you do like this linear like time, like a segment query, I mean segment check. Okay, it actually still take too much time, and also we would like the algorithm to be what we call output sensitive, because obviously from this discussion you can see that, okay, the output size is going to be much smaller than the number of segments, right? So we are more interested in the output sensitive algorithms. Okay. So okay. So let's think about that. Can we have a better data structure that handle this to handle the window query problem? Okay. Of course, this is a simplified window query problem because first I go everything, including the boundary of the window as well as all the segments, are what we call axis parallel, right? So this is obviously a simplified window query problem. Okay, so let's look at this figure. Okay, you can see that, okay, the segment, okay, each segment can lie entirely inside the window, right, like this. Okay, or intersect the boundary of window, okay, once, like for example this one, right? This segment intersect the boundary of the window once, right? Actually, it also includes this one, because this the intersection is here. Okay, okay, or like this one. This one. It intersects with the boundary of window once. Okay, or partially overlap the boundary of window. For example, like this. Okay, or like this. This one. Okay. Oh, sorry, I forgot. I mean, this is intersect with the boundary twice. This one. This is overlap with the boundary of window, and this one too. So we have these 4 different types, right? Okay, for any window query, okay, you want to return any segments, okay, that fall into, I mean, these 4 categories, right? Okay, but the first thing is like this, okay? In most cases, the segment has at least one endpoint inside the window. Okay, so for example, if the segment is entirely lie inside the window, for example, like here, okay, then obviously one endpoint of that segment is inside W, right? Or, okay, it intersects the boundary of window once, okay? Well, for example, like here, you can see that one of the endpoints will be inside the window, right? Okay, or okay, if it partially over that boundary, okay, then well, we probably may not say. We will deal with the other cases later. Okay, for example, like if intercept the boundary twice, then the endpoints are not in the window, right? Okay, so let's try to. This is also kind of like divide and conquer. Okay, so this statement. Okay, in most cases, the segment has at least one endpoint inside W. Actually, it covers the first two cases, right? It covers the first two cases. Okay, so well, let's discuss like how we deal with those cases first, and then we discuss the other cases later. Okay, so well, let's take 10 minutes break. When we come back, we will continue our discussion here.